Hello AP Stats. We are in Chapter 11, Section 1, talking about chi-square distributions and chi-square goodness of fit tests. Here I wanted to kind of review a couple things we talked about in class about the chi-square distribution specifically. Be sure you write these things down. The chi-square distribution we talked about, like the normal distribution, it does have the area under the curve of 1. It's all above the x-axis. Unlike the normal distribution, it is generally skewed to the right, and it only can take on positive values. This is a squared statistic, so it wouldn't be possible to have negative values. Some of the things that we did not talk about in class is the degree of freedom that you are given, which is for a goodness of fit test, the number of categories minus 1 is also equal to the mean of the chi-square distribution. So in this distribution I've drawn here, the mean would be at 5. Another interesting thing is the mode, which would also be the peak of the distribution, is equal to the degree of freedom minus 2. So in my picture here, the mode, the highest point, would be at 3. And so the good thing about that is that when you work out your test statistic, which is the observed counts minus the expected counts squared over the expected, all summed up, if for instance you got a chi-squared of 10.4, you would know kind of how extreme it was depending on what the mean and mode were of your chi-square distribution. So in my picture, since 5 was the mean and 3 was the mode, I know 10.4 is a very extreme test statistic and would give me a low p-value, and so I would probably reject in that test. We also talked about on chi-square distributions, the higher your degree of freedom, the more this is going to shift, and your mean is of course moving out and it's becoming less skewed to the right. So keep all of those things in mind. I want to go through one goodness of fit test here. Several of y'all have read Malcolm Gladwell's book, The Outliers. Great book if you haven't read it. And this is a problem he talks about in that book about birthdays and hockey. In this book, Outliers, Malcolm Gladwell suggests that the hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically because January 1st is the cutoff date for youth leagues in Canada, where many NHL players come from. Players born in January will be competing against players up to 12 months younger. The older players tend to be bigger, stronger, and more coordinated, and hence get more playing time and more coaching and have a better chance of being successful in the long run. To see if birth date is related to success, judged by whether a player makes it to the NHL, a random sample of 80 NHL players from a recent session was selected and their birthdays was recorded on the one-way table below. It summarizes the data on birthdays for these 80 players. So they divided it up into quarters of the year, 32 players, 20 players, 16 players, and 12 players. And when we look at that data, we can see in our sample there's clearly more people that were in the sample born in January to March, but we want to see if that is significant. Do these data provide convincing evidence that birth dates of NHL players are not uniformly distributed throughout the year? So this, whenever it's asked if there's convincing evidence, that means we're going to run a goodness of fit test. So here's the test, and I want to point out some important things to you. Okay, first of all, we want to perform a test of the birthdays of all NHL players are evenly distributed across the 4 quarters of the year. Notice the null is in terms of the population, which is what we've always done. But in a goodness of fit test, a lot of people will miss this part and just say the birthdays of players in the sample, or even if they don't say players in the sample, if you're implying that, then you're not going to correctly be stating your null. So be sure you're talking about all the NHL players. Our sample is just trying to give us evidence of whether or not we can reject this null. So the alternative is the birthdays of all NHL players are not evenly distributed across the 4 quarters of the year. So we didn't have a significance level, so we will use alpha to be 0.05. The name of the test is a chi-squared goodness of fit test. You can also write that just as Chi-2 GOF. That will definitely work as your name of the test. Our conditions, first of all, random. It said in the problem that the data came from a random sample of 80 NHL players. But random in this can be, again, randomly put into treatments or a random sample, either one. You don't have to be very concerned with the independence condition unless you are sampling without replacement, and here we are. So we need to make sure we mention the 10% condition. Because we are sampling without replacement, there must be at least 10 times 80, 800 NHL players. In this season, when the data were collected, there were 879 NHL players. So here we've shown that the population of NHL players is more than 10% of our sample size. And then the last condition, and most important, is the large count. Now, we do not have a normality condition. We don't want the data to be normal. We just need to make sure that the count is large enough that the chi-squared distribution will be accurate. So we need to make sure all of the expected counts are greater than 5. Now, expected counts is not the data we were given originally. It's what we expect each one to be. When we worked with our M&Ms, each expected count for red, blue, brown, etc. were different, and we would have to list those all and show that they were each individually more than 5. Here, the counts for each quarter of the year should be the same. So if birthdays are evenly distributed across the 4 quarters of the year, then the expected counts are all 80 times a fourth, which is 20. These counts are at least 5. So make sure you list all your expected counts. It is not the counts you have observed as your expected counts. So next we calculate our test statistic. You should at least show this formula, the sum of observed minus expected squared over expected. It's also safe to write down a couple. Our expected was 20, so our first amount in January to March was 32 minus 20 squared over 20. The next one in April to June was 20 minus 20 squared over 20, and so forth. So if you want to just show a couple of these, the good thing about that is if you then use your calculator and your test statistic is off, you'll still get partial credit for showing your calculations. So if we decide to draw a curve, and you certainly don't have to, we know our degree of freedom is 3. It's the number of categories, which were the 4 months or parts of the year, minus 1. So that would be 3, and notice that's about where our mean is here. 1 is where our mode, our highest peak, is. And we end up with a chi-squared of 11.2. So you can see that looks pretty unlikely according to our picture. So we can calculate the p-value, and the p-value comes out to be 0.011. I'll do that on the calculator in just a minute. And so here is our conclusion. Because the p-value of 0.011 is less than alpha of 0.05, we reject the null. We have convincing evidence that the birthdays of NHL players are not evenly distributed across the 4 quarters of the year. One thing I want to remind you is make sure when you fail to reject that you do not accept the null. Now we know we haven't had a problem with this before, and it's when we're working with means and proportions, Y'all have been great at not accepting the null, but sometimes when it's worded in this way and you fail to reject, you want to say, it does seem that NHL players' birthdays are evenly distributed across the 4 quarters of the year, and that's not what we're testing. We're testing for evidence to reject, not accept the null, so be really, really careful of that. So let's see it on the calculator. We go to our stats list editor like usual. Let's see if I can. And under list 1, I list, there's the first quarter of the year, 32, 20, 16, and 12. Under list 2, I do the expected. And again, you are rarely given the expected. You're usually given proportions. Another common mistake in chi-square test is people put in proportions. These should not be decimal values ever in a chi-square test. So make sure you do 1/4 times the total 80 for each one. These numbers aren't always the same, only if we think it's evenly distributed, and here we did. So we're going to go to F6 test and go down to chi-squared GOF, goodness of fit test. We put in our observed as list 1, our expected is list 2. Degrees of freedom, again, is the number of categories, which was 4 different times of the year minus 1. And we can draw it or calculate it. I'm going to draw it here. The good thing about the drawing is if you want to just sketch that drawing, that might get you a little bonus, and it helps you understand what's happening. And we can see it's so unlikely we can't even really see the shaded area. Our chi-squared is 11.2, and our p-value is 0.011, which again is less than alpha, so we would reject. Couple more things to remember. To review what we've talked about, make sure you are using counts, not proportions. For your expected counts have to be greater than 5 condition, the large count condition. Make sure you show the expected counts somewhere in that condition. For independence, only worry about the 10% rule if you are sampling without replacement. And for the null, make sure you put it in terms of the population, in this situation all hockey players. And when you fail to reject, make sure again that you do not accept the null in the way you word it. I want you to try this take-home problem I put below. Give it a try and you'll get your answers in class, and but try to be really thorough. Thank you.